So these are the ways of doing a really reasonable study. So we start off with experimental controls. So that includes the subjects who've never been vaccinated, see what the underlying rate of autism is. Because if the ones who've got the vaccine are just the same, then it's not very impressive, is it? Size of study, the more the better as a general rule. Statistical significance. Now this is a very misleading term, and I'm going to go into more detail about this later. It's a very misleading term because it gives the impression that if you find something that passes a test of statistical significance, you've proved it with a sort of some level of compelling level of evidence, and also that it's significant, i.e. we must take it seriously because it's quite a big effect. Neither of those two statements are true. It has a very precise meaning, which even most scientists routinely get round their necks, and we'll be addressing that shortly. But it is, in a very broad sense, a measure of strength of evidence. Random selection to avoid bias, as we were saying, and confounders. If you can, measure other factors that might affect the outcome so that we can detect the effect of some of these things that we suspect could mimic the effect of a link between the two. And that means we need an even bigger sample, because if we're going to slice and dice it and look for, just these sort of people who've got this particular potential confounder, well, they're going to be a subset of this sample that we've got. So that puts even more pressure on getting a huge number of people. And blinding. Now, blinding is very important because notoriously scientists, if they know, often they start, for example, a clinical trial of a new drug, they're very optimistic about whether it's going to work. I've written a paper that appeared in The Lancet with Ian Chalmers that looked at what's called optimism bias. And people go into and set up these studies, and they're pretty keen and pretty enthusiastic about the hypothesis they're testing. And this can cause trouble if you are dealing with a quite touchy-feely concept like autism in terms of diagnosing it. And so when did he first show these signs? They're very difficult. It's not like the ultimate medical symptom, which is death, right? Nice, clear endpoint. Not too much disagreement about that. This is much flakier. And so if people are sensitized to what might be found in a study, that can really affect the outcome. So ideally, we want the people taking part in the study to be blinded to what actually is being looked for. So let's have a look at what actually happened with the study. So on the left, we've got the original Wakefield et al. Study. Actually ended up being Wakefield on his own because all the other authors basically withdrew their support for it when it became clear that it wouldn't go the distance. And this other paper from the Journal of Autism and Development Disorders, published in 2007 by Uchiyama et al. It's a very interesting paper. Unfortunately, it's behind a paywall, so it's quite difficult to get hold of, but I can talk you through it so you can see what constitutes a rubbish study and see what constitutes a really clever way of dealing with these tricky questions. So, experimental controls. Well, Wakefield had none. It's what's called a case series study, where he got a number of children who had autism who came into the clinic and then asked the mothers, basically, did they have an MMR jab and when did they have it? Okay, so it's very, very basic. There were no controls. Uchiyama and his colleagues did something very clever. They exploited the fact that the MMR vaccine was only available in Japan from the late 80s to the early 90s. So before the late 80s, there was no MMR vaccine. Then there was for a few years, and then there wasn't again because Japan switched to separate vaccines, the M, and the R. They separated the three out. And that allowed Uchiyama and his colleagues to do something very clever. They could have a look at the records of children who were diagnosed with autism in those 3 time frames and see if there was any difference, which is really quite a handy thing to do. And they had those who had the MMR jab positive or didn't, those who were diagnosed with autism or didn't. They were both included. So experimental controls, Uchiyama et al. Had them, Wakefield didn't. The size of study, well, as I say, Wakefield et al., that was a case series, and it's just 12. Uchiyama et al., 900 plus. Okay. Little warning, which I'll expand on a little bit later on in the this morning's session. Don't be fooled by the 900, because by the time they'd sliced and diced this into, for example, the 3 timescales, the figures started to get a bit flakier. So don't be blinded, if you're a journalist, don't be blinded by sheer size of numbers. But it is better than Wakefield et al. It's not even possible to do this comparison that you need to do to carry out a statistical significance test in the Wakefield et al. Because there's nothing to compare it with. Whereas Uchiyama et al. Were able to show, by looking at these 3 time periods, that there was no significant correlation between having the vaccine, the triple vaccine, and autism. And that's statistically significant. In other words, if chance were the explanation, it could have quite easily have explained what was actually seen. It wasn't a random selection in either case. Both basically focused on cases that are emerged as a result of a specialist clinic that specialises in autism and looking at the records. So they just went sequentially through the thing. So neither of them were random, but they were, Uchiyama et al. Were able to look at some potential confounders because they had enough numbers, where again, Wakefield wasn't able, maybe willing, who knows, to do that. Finally, were they able to blind, introduce some concept of blinding into the study? Well, the great thing about Uchiyama et al. Is they were looking at records that came from before the time that Wakefield et al. Sensitised everyone to the idea that there was potentially a link between the two. So that was, they thought they'd done a reasonable job in that the mothers who were filling in the questionnaires about their children were blinded to the idea that there might be a link. So that was quite good news. So Uchiyama et al. Isn't exactly perfect. They say in a very extensive discussion section there are flaws with the way they did things, but it's certainly a bit more compelling than 12 cases with no blinding, no possibility of checking if random chance could have explained it, and no chance of investigating other potential conclusions. So that is an example of the sort of ingenuity that scientists have to bring to be able to demonstrate things in a scientific manner. But the take-home message for anyone who has to report science is that The Lancet is a high-profile journal, a high-impact journal amongst academics, whereas I have to say the Journal of Autism and Development Disorders is not. And if you just focus on some of these sort of simplistic views of what constitutes good evidence or bad evidence, you are going to come woefully unstuck. But that said, most people who are involved in reporting science don't get to see the paper or don't get to read it. The Lancet is circulated amongst most of the major newspapers, and And so they do get to see that, but by and large, we don't. What journalists get to see typically is just a press release from the academic institution. And what I want to do after the break is go through a press release from an academic institution and take that apart using the sort of rules that we can apply to a scientific paper to see if it stands up or not. Okay, so we'll do that after the break. Come back at 11:30. Thank you. So welcome back for part two. So as I said, most science stories are communicated to the media and thereby to a wider audience via press releases prepared by the press office of sometimes quite prestigious organisations and academic institutions.